Okay, so part 2 of the thrilling series, How Efficient is a Chemical Reaction? And this is all about atom economy. So part 1 was about percentage yield. And a percentage yield is how good are you at doing your reaction. So you put in all the reactants, you work out how much product you should have got and how much product you did get. So it's how good are you at actually carrying out that reaction. Whereas atom economy is like how good is your reaction in the first place. So in terms of the equation for atom economy, and I'll go through this a few times. So I'll go through the equation and then I'll talk about give you sort of an everyday example to hopefully help. But atom economy, which is a percentage, it's the MR of the desired product, the product you want, divided by the total MR of all the reactants, times it by 100. And so the everyday example I'll use, which I say every day, it's going to be a bit random, I guess, but the everyday example is, let's say you want to make a ham sandwich, but you're a little bit particular, and you only like the end bits of bread, the 2 slices of bread that have got the full crust. So you want to make that. So you get your loaf of bread, but the only bit that's useful to you is the 2 end slices. You buy a pack of ham, which has got 4 slices of ham. So you need to buy 4 loaves of bread. So you've got your 4 loaves of bread, your 4 slices of ham, and then you turn that into 4 full crust ham sandwiches. Should have drawn this beforehand. Loving the drawing. Right. You've got your 4 ham sandwiches, but then you've also got, so these are like, you take your crust and your bit of ham, make a sandwich. Crust, ham, make a sandwich, blah, blah, blah. But then you're also going to have four loaves of bread that are virtually full. They've just had the 2 crusts taken off. And so this is what you want. That's wasted. So these just all go in the bin, right? That's a poor example of economy. Because even if you never make a mistake when you're making these sandwiches, so let's say you never drop a bit of bread on the floor, you never accidentally drop some ham, you don't waste a single crumb of these crusts, it's still a really inefficient reaction because you're having to chuck away all of the rest of the loaves of bread. So the atom economy for this would be pretty poor, because if you imagine, right, let's say you've got 4 kilograms of bread. Let's say you're being incredibly generous with your sandwiches here just to make the numbers easy. You've got 1 kilogram of ham. That is a generous amount of ham in a sandwich. Right, so that's 5 kilograms of reactants. And let's say when you're making this, you end up with, if you're lucky, 0.5 kilograms of crusty sandwiches and 4.5, because obviously 5 kilograms in means you've got 5 kilograms out, right? So you're paying for 5 kilograms of ingredients, 5 kilograms of reactants, but you're only getting 0.5 kilograms of useful stuff out. So 4.5 kilograms of it is just going in the bin every time. So that is a poor reaction. So you've got 2 ways of improving this. You can either change your reactants to try and make your process more efficient, or you can try and find a use for the waste product. Now, let's say you had the miraculous idea of using all of these slices of bread to open up a toast restaurant. Then these are no longer wasted, and you've got 4 loaves of bread just drawn on the floor. This is going to be angry. I hope it remembers that. Yeah, no one will ever know. Right. So now, instead of binning these 4 loaves of bread, you manage to sell them to a toast restaurant. A restaurant that only sells toast. So now you're putting in 5 kilograms of stuff, but you're getting out 5 kilograms of useful stuff. So the atom economy would be 100%. The other thing you could perhaps do, let's say, because there is no such thing as a toast restaurant, so that is all useless. Let's say you just redesign your reactant. So instead of buying ordinary bread, you manage to redesign these loaves of bread so you only buy really small loaves of bread. So you really short loaves of bread. So you still get the crust at each side, but there's far less wasted bits. So that would maybe only be 1 kilogram of bread. So 1 kilogram of bread, 1 kilogram of ham. You get your 0.5 kilograms of sandwich. And instead of wasting all of this bread, you're only wasting the little tiny bits in the middle. So 4 little mini bits, which is 0.5 kilograms. For your percentage yield, your atom economy now is much improved. And I've messed up my numbers. That should be a 1. Right, 2 kilograms of ingredients. This time is giving us 0.5 kilograms of useful stuff and only 1.5 kilograms of waste. So it's much better design. There's less waste. So atom economy. Oh dear. Whoa. Need to get a camera stand. Okay, let's pause. Right, so atom economy, you can improve it either by redesigning your reaction, so you're using less reactants, which makes that number get smaller. Remember, if you divide by a smaller number, you end up with a bigger number. So if you can make this bottom bit smaller by redesigning the reactants you're going to use, that's better. Or you can make the top number bigger. So you can't really increase the MR of the product you're doing the reaction for. But what you could do is, if you can make it so that there aren't any waste products, so that you're able to use all of the products that you're making, then the top number gets bigger. So go through start with a simple example and go through a couple more. So this reaction, you can use methane and steam to make hydrogen and carbon monoxide. So methane is CH4, steam, just water, H2O, and we're making hydrogen, which is H2, and carbon monoxide, CO. Let's balance it. 1 carbon, 1 carbon, 1 oxygen, 1 oxygen, 4, 5, 6 hydrogens. So we need to put a 3 in front of this one. 3 times 2. So that's our balanced equation. The useful product here is hydrogen. Carbon monoxide, not useful at all. Total waste product. Greenhouse gas, kills people. Yeah, just bad news all around. So we can't make that a useful product. So we're looking at this, and we've got atom economy. The MR of the desired product divided by the total MR of all the reactants times 100. Need to use a periodic table for it. I haven't got one to hold up. I'll attach one to the sheet you're going to do, but those are the only elements we're going to look at today. So CH4, so we've got 1 carbon, which is 12, 4 hydrogens, so 4 lots of 1. So we've got 12 plus 4, so that one is 16. H2O, 1 plus 1 plus 16, so that one is 18. H2, 1 plus 1, so it's just 3. And CO, 12 plus 16, so we have got 28. Right. So those are the MRs. We're going to use the big numbers for this time. So the MR, 16, 18, 3, 28. We're making 3 lots of this one. So the MR is only 3, but so 3 times, that's a 2. 3 times 3. So that equals 9. So if we look at that, 16 plus 18. So we are putting in 34 in terms of the reactants, and we are getting out, and I've massively messed up my numbers here somewhere. Oh, right, maybe I'll edit this bit out of the video, because H2 is 1 plus 1, which equals 2. So then 3 times 2 equals 6. So 6 plus 28 equals 34. So we're putting 34 in, and we're getting 34 out. Conservation of mass. Can't create any matter, can't destroy any matter. Just rearranging it a little bit. So we put in 34, we get out 34. If we go back to this one, so where it says the total MR of all reactants, you sometimes will see that written as the total MR of all products, because they're exactly the same. The total MR of all the reactants, 34. Total MR of all the products, 34. So they're interchangeable. So if we're going back to this, I don't know why I rubbed all that out. CH4 plus H2O goes to 3 lots of H2 plus CO. Right. The useful bit, 3 lots of H2. So we worked out the MR of H2 was 2, but we get 3 lots of it out. So we are getting 6 grams of useful stuff. We are putting in 34 grams of stuff. So 6 divided by 34 times 100 gives us our answer, 17.6%. So the atom economy for this reaction is 17.6%. Pretty low, because for every 34 grams you put in, you're only getting 6 grams of useful stuff. It's actually pretty tricky to improve this, because you can't find a use for carbon monoxide, and there isn't really any other way of turning methane into hydrogen. So it's just a poor atom economy for this reaction. If we're going to look at a different reaction for atom economy, so we're going to try and ferment some sugar, glucose, into ethanol, alcohol. So the reaction for that, so we start off with our glucose, which is C6H12O6, and we are going to turn that into CH3CH2OH. That is ethanol, and we also turn it into carbon dioxide, CO2. And we balance this one, and we get 2 of those, and 2 of those. Don't worry, you do need to balance equations, but in these sorts of questions, they'll give them to you balanced. They'll also give you the MR, most likely, in these questions. So we've got our we've got our glucose. We're going to turn it into ethanol. So that's the reactant, that's the useful product. And when we're doing this, we need to work out the MR of this. So we've got 6 lots of carbon, so 6 lots of 12, plus 12 lots of 1, plus 6 lots of 16, that's 180. We've got 12, plus 3 lots of 1, plus 12, plus 2 lots of 1, plus 16, plus 1, that equals 46. So we're putting in 180 is that, 46 is that, but actually we're getting 2 of these, which is quite useful. So we're getting 2 lots of 46. So we go back to our atom economy. So atom economy equals the useful stuff we get out divided by the total of all the products, or, because we could add that one on, or we can just do the total of the reactants. So the useful bit is 2 lots of 46, and the total products we're putting in is 180. So 2 lots of 46 divided by 180 times by 100, and you end up with 92 divided by 180 times 100, and you can tell it's going to be just over 50%. And the answer to this one is 51.1%. So 51.1% atom economy for this one. How could we improve it? If we could find a use for carbon dioxide, you could improve it. So let's say you open a fire extinguisher factory, and then you can use the carbon dioxide to fill up the fire extinguishers. Or maybe you sell the carbon dioxide to Coca-Cola so they can use it to make the drinks fizzy. Then this would no longer be a waste product. So just doing this example again, let's say you do open, Jeffina manages to open her fire again. Oh dear. Right. Jeffina manages to open her fire extinguisher factory. CO2, C is 12, O is 16, so it's 12 plus 16 plus 16, so that is 44, but we've got 2 lots of 46 and 2 lots of 44. So the total we'll put in is 180. This is useful, the ethanol, because that's why we're doing it. And then because Jeffina's opened her fire extinguisher factory, that is now useful as well. So the total we're putting in is 180, but the total useful that we're getting out, that's 92, that's 88. 92 plus 88 is 180 times by 100. So that is 100%. So if you found a use for all the products, your atom economy is 100%. That's also why, and sometimes you get a trick question, if there is only ever one product, so if you had a reaction that was A plus B goes to C, what's the atom economy for that? You don't need to know anything else you don't need to know the MRs of any of them. The atom economy must be 100%, because there's only one product. So everything you're making is useful, so it must be 100%. Hopefully that's made sense. If not, send me an email and I'll talk you through it. Thanks. Bye.